So a polygon is any closed plane figure formed by 3 or more segments that intersect only at their end points. It's a really elaborate way of saying it's a shape. It has to be closed. So if it's open, it's not going to be a polygon. Okay. If we have segments that intersect, saying like that would not be a polygon because their segments intersect each other. So this is a polygon. So we have vertices, diagonals, and sides. So sides you've been doing since elementary school. How many sides does this figure have? 5. So that means it's a pentagon. It is a polygon too. And then how many vertices does it have? 5. We learned that in our investigations. However many sides is how many vertices it's going to have. So that's all of these points where they intersect, right? Yeah. Diagonals might be somewhat new in this context. So diagonal is from any vertices to any non-adjacent vertices. So that's when you, so if I had from E, if I went to A, is that a diagonal?
No.
No. Why is that not a diagonal?
It's adjacent.
It's adjacent. Okay, so from E I could go to B, I could go to C. Could I go to D? No. Okay, so those are our diagonals. So the first way we classify polygons is by the number of sides. So we have triangles, quadrilaterals, pentagons, hexagons, octahexagons. These all, you're going to have to know these shapes. That's in our vocab box, right? So that means we need to know those vocabulary words. So if I ask you what's a nonagon, how many sides does that have? 9.
Oh.
What about a dodecagon? 12. 11 is a hendecagon.
Why is it not on there?
I don't know. I screenshotted that from the textbook.
So past 12 is going to be an n-gon. So you replace n with how many sides? So a 13-gon, a 14-gon, a 17-gon.
Parker, Michael.
Second way we classify polygons is by their concavity. So if they're concave, like this quadrilateral, kind of makes that cave, right? Sinks in. Or convex, that's the ones we're used to.
So that was some of the words you guys weren't sure about. You've learned them before, but it's probably been a while.
Okay. So we can tell a concave quadrilateral or any polygon is if their diagonal goes outside. So see how this diagonal goes outside of the polygon? That's how you know it's concave. Okay? Even though this diagonal stays inside, they have one that goes outside, so it automatically makes it concave. Okay. Convex, every single diagonal has to be inside the polygon. So you have these on your notes. Go ahead and see if they are a polygon, if they are classified by sides and concave or convex. Alright, for our first one, it has how many sides?
6.
6 sides. It is a polygon because it's closed. None of the segments intersect. 6-sided, so it's a hexagon. And it's also convex because there's no diagonals that would cross or go outside of the polygon. Our second one, the moon. Why is that not a polygon? It's rounded. That means it's not made up of line segments. Segments have to be in a straight line. Okay. This one, I don't know what this one is. It's obviously not a polygon. Colin, why is it not a polygon? It's not closed. Okay? If it was closed, it would become a polygon. Arrow right here. Concave, because we have a diagonal.
I need to go back and resave this line.
We have a diagonal right here that goes outside of the polygon. That's good. But it caves in, so you can see that it's concave. And how many sides does it have? 7, so it's a hexagon. And this little shape right here, 17 sides, so it's a 17-gon.
No, I was kidding.
Next way to classify polygons. So first we have by number of sides, then we have concave or convex. Now we have regular or irregular. So to be regular, it needs all congruent sides, so it has to be equilateral. And it also needs to have all congruent angles, means it's equal angular. Okay, so how do we mark that? You have this diagram on your notes. So go ahead and mark that as equal angular and equilateral. So how do we show that? What shape is this? A hexagon. How do we show this hexagon has the same size, Sean?
You put like a tick mark on each side, and then on the angles you put like the.
That's gonna be a sec.
Like,
Is he drawing it like an arc?
yeah.
That's how we know that this is a regular hexagon. Okay? Now I want you to take like 90 seconds and think about this question. Can we draw an equiangular hexagon that is not regular? So if it's equiangular, that means that all the angles are the same, but it's not regular. So what do we know about sides? We don't know the sides are equal. Okay, so think about it. I don't want to hear any talking. I want you to like critically think for a second.
You got it?
Alright, so now we have an application.
Just got a
of
few
our
more
polygon.
examples. Listen up. We're almost
So
done.
we have a head of a bolt that's shaped like a regular hexagon. So right here we have a hexagonal bolt. That's how we call it. It's a hexagon. And we know it's a regular one. So what do we know about the size of our hexagonal bolt? They're equal, right? So I can kind of label that on the diagram. You have this on your notes too. So how can we find what the length of our one side is? Give me enough information.
7.1.
What'd you say,
X
Colin?
equals 4.
That's looking at the angles. So now we're looking at the sides. We don't really care about the angles for this problem. What'd you say, Lily? You can set them equal to each other. They're the same length, right? So if I have one length that's the same as another, not earlier when we were doing proofs, say 4x plus 3, is that equal to 5x minus 1? Do a subtraction code, get all the x's on the side, add 1 to both sides, and then x equal. Are we done?
No.
Nope. Always look at what the question's asking. So we're trying to find the length of a side. So it doesn't matter which one we put it into? No. So I'm going to choose the 4 times x. I'm going to go ahead and put 4 in there. Plus 3. So that makes it 16 plus 3. Is 19. Now what would happen if we put it into the other expression that we were given?
It's 19.
It'd be the same thing, right? They're regular. They equal each other. Okay, so 5 times 4? 20 minus 1? Minus what? 19.
Yeah.
That one. So that's a nice way you can check your work on that. So during our investigation, our discovery worksheet this morning, know that the sum of the interior measures of a convex polygon, you can draw the diagonal, so when you triangulated this morning, you found how many triangles fit into each polygon, right? And from there, we filled out our table, so we have the number of sides and how many triangles it takes to make that polygon. So if we had a hexagon with 6 sides, you know, we can make that by combining 4 triangles. Okay, and then we found our pattern. So n minus 2 is how many triangles times the measure angle of a triangle, which is 180. So you can kind of apply that to any polygon. That's our polygon angle sum theorem. So just like our triangle sum theorem, where we set things equal to 180 because it was equal to the interior angles of a triangle, you can apply that to any polygon now. So we're given, this one's on your notes, so the sum of an interior angle of a convex heptagon. How many sides are in a heptagon? 7.
7.
7 sides. So how can we find the interior measure? So what's our formula for that?
7 minus 2.
7 minus 2 times 180. So 7 minus 2 is 5. And then you simplify. Now can we find the angle measure of each angle by dividing by 7? Is that legal to do here? Legal. We don't know it's a equal angular heptagon, so we cannot do that. It could be like some funky shape, like if you have obtuse. It doesn't all have to be
but I can't
equal
touch
on
it.
this one.
On the TV.
Okay, so we know the sum of the interior angles is 2,520. But we know it's regular. We're given this piece of information. So that means all the angles are the same, all the side lengths are the same. So since we know the angles are the same, are congruent, you divide it by 16, so you should have gotten 157.5 degrees. So this one works kind of the opposite way. We're given the total sum of the angles, and we don't know what kind of polygon it is. So we know the sum of the interior angles. What do we know about the sum of the interior angles from our investigation? Yep, so however many sides minus 2 times 180. Then we have the word is. What is in math? How do we write that like mathematically? Equals. And then we have 756. So we have what it equals. The hard part of that is just kind of setting up the equation.
This is one of those ones where we're going backwards. We don't know the number of sides. We know the total. We have to work backwards using algebra 1 to find n.
So how can we cancel out the 180? 5.
You want to do that first before you can mess with the parentheses, right? You have to get the 180 out of the way first.
We're left with n minus 2 equal to 42. Last step, add 2 to both sides. Oh. So what kind of polygon is this one? 44gon.
Good job.
One last example, it's a lot like the ones this morning. Let's try it. So it's a pentagon. So how many, what's the sum of the interior angles? 540. So once we know what the sum of the interior angles is, what's our next step? Gotta add all of these up and set it equal to our 540. What does C come out to be? 4.
Yeah, there's 135 total C's.
Get C all by itself. Now with that C, we can find each measure of the angles, because that's what it asked for at the beginning. It said find the measure of each interior angle. So it wants to know what angle A is, what angle B is, and so on. So with C, put it back in. So angle A is 35 times 4, which is calculator right in front of you. 130. B is 18 times 4. And we kind of get a freebie because B and E are the same.
A should be 140. Yeah, A is 140.